We can now look at some examples, and we're going to look at an example with point charges, and we're going to extend the example that we did in chapter 21, where we had 2 point charges and we were looking at the electric field at 2 points based on these 2 charges. So I'm going to bring up this diagram, probably recognize it from chapter 21. And what we're interested in finding is the potential at point A due to the 2 charges and the potential at point B due to the 2 charges. And we're going to look at this in 2 different ways to show that either way you calculate it, it will come up correct, as long as you do the math correct. So let's get the values of the electric fields at those points. And from chapter 21, we found that the electric field at A due to 1, charge 1, was equal to the vector 1.081 times 10 to the 6th and negative 6.2234 times 10 to the 5th newtons per coulomb. And the electric field A2 is equal to 0, comma, and 4.995 times 10 to the 6th newtons per coulomb. So now I want to calculate the potential due to, at point A, due to charge 1, and that's just going to be the magnitude of the electric field times the distance between R1 and RA. The magnitude is going to be the square root of the squares of the 2 components it's just Pythagorean theorem, and the distance is between Q1 and point A is 60 centimeters, which is 0.6 meters. And I should put the units here. The units are going to be newtons per coulomb when I get done. And this is going to be 0.6 meters. And that's going to equal, well, I need to calculate this Pythagorean relationship here. So I'm going to get my calculator out. Okay, so that's all typed in, and hit enter, and I get 1.248 times 10 to the 6th. Newtons per Coulomb times 0.6 meters, and that is going to equal 7.489 times 10 to the 5th volts. Volts is unit of electric potential. And its unit designation is V. Okay. Now I'm going to do the voltage due to charge 2, and that's going to be the electric field magnitude times the distance. Well, the magnitude is easy because you have a 0 here, so it's going to be 4.995 times 10 to the 6th. And the distance from charge 2 to A is 30 centimeters, so that's 0.3 meters. I forgot to put units in here again. Should always try to keep units here. And that gives me 0.499 times 10 to the 6th volts. Now, my potential at point A is just going to be equal to my potential at point A due to charge 2 minus the potential at point A due to charge 1. And if you subtract those two numbers, you get 7.497 times 10 to the 5th volts. Okay, so let's look at it from the standpoint of the other formula that we had. So we had potential VA1 is equal to, we got Q over 4 pi epsilon naught times the distance R1 minus RA, that's equal to, that was 50 millicoulombs, or it's 50 microcoulombs, and that the Q1 was negative. And the distance was 60 centimeters, so it's 0.6 meters, and that gives me negative 7.489 times 10 to the fifth volts. And for VA due to charge 2, we use charge 2, 4 divided by 4 pi epsilon naught, the distance from charge 2 to point A, and that's going to be equal to, we had 50 times 10 to the minus 6 coulombs over 4 pi epsilon naught, and here our distance is 0.3 meters, and this equals 1.499 times 10 to the sixth volts. And if I take, in this first part, we took the direction of the vector, and that's why we did a minus. In this case, we're going to do a plus because we took into account the charge polarity. And that's going to be equal to 7.497 times 10 to the fifth volts. So we've done point A. We can also look at point B. I'm going to let you look at the notes to see how that's done. But you'll notice that at point B there is no potential because it's symmetric. So along this line, the potential is 0 along this center line because everything is in symmetry. So that line will have no potential along this line.